between the two? Might not seem like much.
Wait. What?
You, traveling at 10% the speed of light, have aged 0.6 seconds less than the person who was here at school already.
Loser.
Wait.
It's by Sonic's
What?
So,
Immortal.
yeah.
That's what this class is all about.
No wonder Sonic looks so young.
Good Sonic's in.
If you were traveling at, say, 0.9 times the speed of light, and you're in a spaceship, you travel to a foreign place, you come back, a foreign planet, you come back. Let's say that people on Earth, you have your identical twin who stayed behind on Earth while you traveled to the rocket. Your identical twin, aged 1 year. How old are you now? Well, that's equal to how old you are.
How many
Over
markers
the
did
square
you
root
think
of 1
Einstein
minus
went through?
0.9 squared.
How many markers do you think Einstein went through? Let's look that up.
So that's
Really
V
funny.
is equal to
Chalk.
0.9 times the speed of light.
So how does distance affect this, or is it just like how fast you're traveling?
How fast you're traveling. The distance would affect how long you're gone, in that sense.
5.26 years.
Yeah, that something's wrong.
I got, 0.435 years.
I got the same.
436.
Yeah, my bad, 436.
Your identical twin is now more than a half year older than you are, biologically. This is the implication of the speed of light being the same in every reference frame. And the reason you've heard of Einstein is because this is correct. There was no evidence of this until 1941. I think the experiment was done in 40 and it was published in 41. That's the first time there was actually experimental evidence to support this.
How do they do the experiment to support it?
All right, so it's called the muon experiment, done in Mount Washington, which I now know because of the weather up there recently, that it's the tallest mountain on the East Coast. Something like that.
Wow.
What? Okay. I thought we had the tallest mountains.
Maybe it's the tallest one in the Northeast. But- So they have this thing called muons, and a muon is a particle comprised of, I think it's an up quark and an anti-up quark.
Oh,
Really small.
No, it would not be. It'd have to be. To be positive, it would need something slightly different. But yeah, it's a small particle. It's on a crude scale. Think of it as suddenly blanking on the numbers now. It's about very crudely on par with the thing about size of a proton.
Okay.
They're not particularly stable. If I have a muon here, it's going to decay into other things. So you go up the top of Mount Washington, you check the muons that are coming in from outer space, and you count how many are there. You count how many muons are passing through. You then go down to the bottom, so you're farther away from the sun, you count how many muons are down there. You make two predictions. You make a prediction based upon special relativity is all bunk, and you make a prediction based upon special relativity existing. If special relativity is bunk, I think this was around 500 muons up here in an hour. The prediction was it's like 300. We'll go through the math later, but 300 per hour is prediction without special relativity. For with special relativity, the prediction was somewhere around 50 per hour, so very distinct differences in the predictions, and they almost hit it perfectly. So,
I feel like you could do a cool like twin problem with this. Maybe not this class or whatever, or whatever, wherever it's applicable. And just, you know, like if there's, cause I have twin brothers and I just keep thinking about like if. I'm
Want
trying
to change their age?
I'm trying to think of
She
like
wants to shoot one of them
like,
into
let's
space.
say one becomes an astronaut, right?
Yep.
And somehow we've managed to come up with a way to travel at the speed of light, somehow.
okay,
Yeah, and like, the one who's an astronaut takes a trip that lasts 2 years, like, or.
then it
you
becomes
can-
his time or the Earth time,
Yeah, can I ask you a
it
question?
should be different, yes?
So like to the person, I guess the box frame, for them, the time is the same. So it's like you're aging less, but from the box's point of view, you're fine.
Yeah, you don't, I mean, the person on the Earth and the person in the spaceship are not noticing, to them, time is still passing just normally as it would.
So if
So
you were,
You're good.
if you had like a year, and that was like a year to, I don't know, let's say, like count to 1 million, see how far you can get, or
Right.
like see how high you can count it in a year. And so if you're moving faster, you could count, I guess you can get more counts in.
When you get
Yes.
less counts?
Yeah.
Okay.
I'm trying to think of, like-
Well, I mean, if it's, how long does it take you to get there? Well, strangely, all right, so we got the two twins, one goes off on a rocket, comes back,
Mhm.
and he counts, let's say, 1,000 numbers per minute. The twin back here was also counting 1,000 numbers per minute. But when it comes back, he's had more minutes than he
Yeah, so
has.
who counts to the higher number, I guess?
The person who's counting the higher number is the person left behind.
Okay, and then like, let's say like my
Makes
brothers,
sense.
yeah, so like, one of them is traveling at the speed of light, and their trip takes them 2 Earth years. What is like, as far as like age goes, how would their ages compare?
Well, it comes down to how fast were they traveling.
Let's just say speed of light.
If they're traveling the speed of light, then by the time they stop traveling the speed of light, the entire universe would be gone.
Or that.
Wait,
Because wouldn't that make the denominator zero?
Time does not pass. Things go at the speed of light, time does not pass.
Okay.
Would that make the denominator 0 in the
Yeah.
equation? Okay.
What about half the speed of
Half the speed of light, then
light?
just
We would just replace that.
stick a point, put point five in there. All right,
Is that why it's always been like, if you can theoretically go faster than the speed of time, the speed of light, you can technically go backwards in time?
all right, so let's talk about that a little bit. First, a couple things on this, that V over C shows up so much that they gave this, this is called beta. So if you see a problem where it says beta equals 0.5, that means you're traveling half the speed of light. Beta is equal to 1 speed of light. 1 over the square root of 1 minus beta squared shows up so often that they gave that a special name, a special symbol, that's a gamma, lowercase gamma. And this is known as the Lorentz factor. Lorentz had done almost all the math required, but just refused to make that last leap of the speed of light being the same regardless of the reference frame. If you're in a car going near the speed of light and you turn your headlights on, from you in the car, it looks like the light's leaving the car at the speed of light. From someone in front of you where the light's hitting them, to them it looks like the light's still going the speed of light. All right, so, forgot where I was going on this one.
Lawrence had that last little bit, but you want about it.
Yeah, no, there was something I was gonna do right before that.
Backwards in time?
Now, there we go,
Yeah.
okay. So we have this time is equal to the proper time over the square root of 1 minus beta squared. If you were traveling the speed of light, you get a 0 in the denominator, because beta is 1. The math people have not figured out how to do this. They've fallen down on the jobs. They don't know how to divide by 0. But because of this, the theory is, if you start out slower than the speed of light, you will not ever get to the speed of light. You can't, it's a barrier. You can't go past it. So the common way that I usually hear you're in a car going the speed of light, you turn the headlights on, what happens? You've already broken one law of physics right there, so I think there's a video on this, but how many laws of physics do you want to break in order to get an answer? You can go near the speed of light, but you can't quite get there. So in Galilean relativity, if I applied a force to an object, and that if I looked at velocity versus time, and apply a constant force, it would look like that. Apply it long enough, I can go as fast as I want. In special relativity, there is a max value here. And you'll just get closer and closer but never actually hit it. Think of it this way, as your mass increases the faster you go.
So that asymptote, what is that?
That's the speed of light.
Your mass adds as the faster you go?
The mass increases the faster you go.
Wait, could you,
If you don't start at that,
elaborate
you'll
on that?
never get at that.
If I apply a constant force to an object, the only way that my acceleration can drop,
Oh,
slips dropping,
yeah,
is for my mass to increase.
okay.
Oh, okay, that doesn't make sense.
Oh, I get what you're saying.
Just get-
So as you approach the speed of light, you increase in mass, which would then make it impossible for
Right.
you to ever break it.
Yo, mama's so fast, she broke the
Okay, but, all
There we
right.
go, some physics. Go on. All right, now,
So-
theorists who
Wait.
basically need to publish, so they make stuff up, and some of them turn out to be right, and they get the textbooks, and some of them, most of them are just completely wrong.
You publish that.
Raphael, you were about to
So
ask?
if you start at the speed of light, can you ever leave the speed of light?
No.
Oh my god.
If you start, can you exceed it though? If you
No,
start at
alright.
the speed of light, can you exceed the speed of light?
If you start faster than,
If you start exactly at,
no, if you start at the speed of light, that's,
that's it.
yeah,
That's what you're at.
yeah.
Alright.
All right, so now, suppose, so the theorists come along and they look at this and they go, okay, I'll buy the equation. I can't take any object and get it faster than the speed of light. But suppose there's an object that's already starting faster than the speed of light. If I have an object faster than the speed of light, then well, in essence, that number will go slower, because I can't get 0 in the denominator.
Yeah.
I can get an imaginary number, but not 0.
Alright.
The theoretical particle that does this is called the tachyon.
Tachyon particle.
Yeah, tachyon particle.
That.
It shows up in Star Trek a lot. Now,
Pretty big plot point in Watchmen.
if I shot you with a tachyon gun, you would be hit by the bullet before I pulled the trigger. So,
I'm sorry, what?
Uh,
So I'd already be dead by the time you pulled it.
yeah. But if I don't pull the trigger, you're not dead.
But how does that work?
So how does it know you pulled
Yeah.
the trigger?
So,
That's
what
okay.
I'm claiming is that you wouldn't be traveling backwards in time or anything like that. I'm saying that we need to redefine time if this exists.
Wait,
Yeah.
so it basically acts as like a time skip.
You,
Yeah, I guess in some sense.
I get what you're saying.
So
But
you
time
can't go
doesn't
back
really-
in time. You can skip
Time
through
doesn't exist the
time.
way we know it, if that's
However,
true.
Yeah, fine. At this point, it is pure theory. They have not found one.
Right.
time?
Tachyon.
No,
Oh,
it's
I
not.
was.
It's just theoretical.
have
like,
you
that's what
seen
they call
Tenet?
Have you seen Tenet?
Yeah, Tenet. Yeah, with Christopher Nolan's movie. You should watch it. It's pretty interesting. They have a lot of like concepts like the gun shooting and then it's already the bullet's already there, or the gun being shot and then it's reversed out of it. It's pretty cool. You can watch it reversed and it's the same movie, I guess.
Well, the Buzz Lightyear movie went over, like when Buzz went up, he was like the same age, and then everyone on the planet aged super fast and died. It was
Yeah.
really
Well,
sad.
he doesn't age as fast.
Or yeah,
Yeah.
but it was super sad.
Mhm.
I
Oh,
thought.
that is sad.
There is a children's story A student said, gave it to me, she said, this book just creeped me out. It was a book by Brian Greene, who's a well-known physicist.
The Crash Course dude.
We love
And-
the greens.
It is
My bad.
it's one of those big, thick books that children have, the one with the big, thick cardboard pages.
Oh, yeah.
Oh, yeah.
So that's why you think it's for a kid. And there's a person in there who travels near the edge of a black hole and then comes back, and so the next line after going around the black hole comes back, so he radioed to say, hey, I did it. And there was no response. And it turns out everyone he knew was dead because time did not pass fast for him,
That's
but
so
everyone else thought it was.
So sad.
It's a good book.
That is awful.
Wait a minute.
And then you say, good night, child.
So theoretically, we can never be able to approve it because by the time somebody would successfully do it, we'd all be dead.
Well, you would have to do it in shorter bursts. He was there too long. I mean, if you went there for, say, 1 second and then came out, then you might be able to notice.
But then how would you be able to do it that
My
fast?
music, right?
Like, you'd have to time it.
Well, the trouble is, we cannot get things that fast yet.
Mhm.
Now, in terms of, all right, special relativity, it's great, it's theory, it's kind of fun, or scary, whichever way you want to look at it. But how does that impact us? GPS satellites, even though they're traveling at a certain speed that ordinarily you wouldn't worry about time dilation, but there's enough of a difference, I think you're off by like 30 feet a day. If you don't take into account special relativity satellites, your GPS would be off by about 30 feet every day.
That's why it tells me to go left when I'm on a cliff and I have to go right and the edge is.
Well, they do take it into account though.
What about the older ones?
No, they still do.
Is it
I think they figured this out beforehand.
Okay.
But there's special relativity, time dilation from special relativity, and then general relativity adds another time dilation factor, and they take both of those into account.
Mhm.
Just the general relativity stuff is,
Brain hurt.
general relativity is the course that just kicked my butt in college. So,
Dr. Fox, can you theoretically see something that's gonna happen before it actually happens? Scientifically?
no, because to do that, are you talking about premonitions or physics, or
Like-
science fiction or fantasy?
Talking about the downfall of society, man. You see that?
More
Yeah, we can see that happening.
like,
Turn the news.
Sorry, there was a Superman comic that I read going as a kid, and they talk about, light bounces off us and goes out into space. And so Superman then travels and then to capture some of these images. But to do that, he has to travel faster than the light is traveling. In other words, travel faster than the speed of light.
mhm.
When we all know he's only faster than a speeding bullet, not light.
Well, that comic just made it canon. You got to accept that.
Oh, okay. So you'd have to travel faster than the speed of light to see the light coming off, to see the light, to perceive the light waves bouncing off of whatever you're gonna see. Anyway,
That's a hard thing to think about.
so when I first was doing this course, I get to this point, we then start doing special relativity, and then I had a student, after a couple of years, a student with NC State, and said, it would really be nice if you had done more time on this other stuff. So we're gonna drop back, we're gonna come back to special relativity, I presumably will have time, but tomorrow, we're not gonna do special relativity. We're gonna talk more about Faraday's law, motional EMF, not emotional, but emotional EMF. And then we'll eventually get back to general relativity, or special relativity.
Sounds like a deal.
Sounds like
You should make like Bill Nye videos, but for like adults.
That's,
I feel like you're the adult Bill Nye.
huh.
That's a good thing.
Although strangely, I was wearing a science rules shirt one day, and there were these 3 teens who were all dressed in all black, doing that real goth thing. And they see my shirt, and one of them goes, "Oh, Bill Nye, he's the best."
Yeah.
I thought,
Dude,
okay.
everyone loves Bill Nye, like all kinds of people. Now that like, I don't know what network he was working for, where